Good afternoon to some, good evening to others, and good morning to some others. We appreciate all the attendees that have joined us today. My name is Adam. I'm the sales manager, and I'll be tagging along in this webinar today. Arvind Krishnan, he's the product manager and the app engineer that's going to be presenting this webinar today. And today we're going to be talking about modeling inductors EMS. As you all may know, EMS is a full 3D FEM package that is fully integrated inside SolidWorks as a 3D CAD. And that's what Arvind is going to harp on and speak about. This webinar will be recorded, so attendees and people that haven't been able to attend but registered will be able to access it later. They will be sent a copy, and I hope you guys enjoy it and you come to learn a few more things that's going to help you in your design scenarios and your analysis. And I hope the product proves to be handy, and some good impressions and conclusions will come out of this, and some good guidance as to what the technology is heading as far as induction modeling and modeling inductors in EMS and FEA overall is concerned. Now let's go ahead and now make Arvind, the product manager, the app engineer, the presenter, and give him the screen to start this webinar right away.
Thank you, Adam. Good afternoon, good evening, and good morning to all our viewers today. My name is Arvind. I am a product manager here at EMWorks, and I will be going through the presentation of this webinar for you. Okay. Now, as Adam mentioned, this webinar is indeed recorded, so please feel free to share this recording once you get an email from us with your colleagues or others whom you think might benefit from this. Okay. Now, as we proceed through the webinar, I understand that some of you might have questions, so please feel free to type in your questions using the GoToMeeting chat box, and towards the end of this webinar we will be making sure that we answer all of your questions. Okay. And let us look at the agenda for today. We're going to start with the company EMWorks, its products and its applications. Then we will jump into the topic for the day. We will talk briefly about inductors, what kinds of inductors are there, and some of the prominent applications of inductors. Okay. Then we will go to why use EMS to study or simulate inductors. Okay. And these things will be very brief, and I would like to devote most of my time towards giving you a live product demonstration that probably deals with a couple of commonly used inductors so that you can get an idea of what the product can do. And finally, we will have a Q&A session and a closing remarks from our sales manager, Adam. Now let me quickly start with EMS products and bundles. EMS is a product 3D FEA electromagnetic simulation product from EMWorks. Now EMS products are CAD embedded products. What do you mean by that is they are completely integrated into popular 3D CAD packages. And three of the CAD packages that we completely integrate into are SolidWorks, Autodesk Inventor, and SpaceClaim. However, today I will be mainly concentrating on EMS for SolidWorks. But nevertheless, the features that I show you and the and all the functionalities are prevalent over all the three CAD packages. Okay. As far as the EMS bundles are concerned, we have EMS Professional and EMS Premium. Now EMS Professional is in turn subdivided into EMS Magnetic and EMS Electric modules. In addition to this, we have several add-on products such as coupling to thermal analysis, coupling to motion, structural, etc. Now we have EMS Premium package, which really is everything, everything that you see on the leftmost side, which includes EMS Magnetic, Electric, coupling, all the coupling analysis, and also a feature called parameterization, which allows you to see how the results vary as per the geometry parameters. Okay, that's EMS Premium. And we also have a high frequency package. We also have a high frequency package for RF and microwave that talks about resonance, S parameters, and antenna. Although for today's webinar, we would just stick to the low frequency electromagnetic simulation that you predominantly see over the right, over the left. Sorry. Now let us look at some of the application areas that EMS covers. Okay. Now EMS covers from low frequency right from DC voltage all the way to few hundred megahertz in the EMS product. Okay. And that covers a wide plethora of application areas, right from automotive, transportation, aerospace, energy, life sciences, process equipments, etc. Okay. Briefly, if you talk about EMS, can deal with linear actuators, motors, etc., solenoids, magnetic levitation, loudspeakers. That's more on the electromechanical side of the application. More on the electromagnetics, that's kind of what more we will be looking at today, is coils, inductors, permanent magnets, etc. Also power electronics, inverters, transformers, conductors, bus bars, inductors, etc. All of them can be analyzed and simulated inside EMS. Okay. As far as our high frequency product is concerned, it ranges from a few hundred megahertz all the way to a few hundred gigahertz. Okay. So this is where RF and microwave products are. Not really the topic for today, but should you have interest in these, please don't hesitate to contact us, and we'll be happy to organize something for you to show you what our capabilities are in that area. Now, as far as high frequency is concerned, mainly we talk about RF and microwave passive components. We're talking about couplers, filters, again RF inductors, signal integrity, and so on. Okay. Now let us briefly look into the type of inductors that we can solve using EMS, mainly in the low frequency domain. Okay. What are inductors? Inductors are basically, I mean, an crude form definition are these are devices that can temporarily store energy. Okay. And mainly the energy is stored in the form of magnetic field. So as you excite the coil, there is magnetic field created, and that this device actually stores energy in the form of magnetic field. Now, three common types of inductors that you will see in the market are air core inductors. You have core, which is some kind of a ferromagnetic core inductors, or laminated core inductors. Depending on the application, any of these inductors could be used. Obviously, the laminated core inductor, which has the best performance and probably is suited for certain application which demand that kind of performance. As far as the air core inductor goes, that is in the other end of the spectrum. Obviously, air doesn't have that good of a permeability, and hence the magnetic field that is actually stored, the stored energy is not that good when compared to either a ferromagnetic core inductor or a laminated core inductors. Now, inductors feature themselves in a wide variety of applications. Okay, as I said before, their primary functionality is to store energy. So all kinds of energy storage devices make use of several inductors in them. In addition to it, transformers, filters, sensors, motors, there's quite a lot of application which does use inductors. Now, why EMS? Why is it an ideal tool or software where you can use to design and study the performance of your inductors? Now, EMS can actually help you to calculate the magnetic field distribution, the induced currents, etc., inside your model. Number one. And then with respect to the solid losses in the core and the winding losses in the winding, EMS will be able to calculate and compute those as well. Okay. Now you can include the effects of laminations in the core in your solution, so that makes it a lot more real life, and you can solve a lot of real life inductors which include laminated cores. Okay. Now, as far as the engineering quantities that EMS can calculate, it can calculate the inductances, the induced voltage, flux linkage, etc., all the electrical parameters and circuit parameters that are associated with inductor models will be computed by EMS. Okay, and finally, if you have high current or high voltage situation where there is excessive amount of induced currents in the core, one may be able to, one will probably worry about the temperature distribution and the heat produced as a result of this. So finally, EMS has multiphysics capabilities which couple it to thermal simulation that will actually help you to compute the temperature distribution in the core due to the induced current. So these are some of the reasons why EMS is a good tool when you want to design and simulate inductors. Now with this brief introduction, let me jump right into the product. We're going to show you a couple of demonstrations that walk you through two different models, and that gets you, to see EMS upfront. Now with that, let me just go over and take a look at the first model of the day. Now here is a ferromagnetic core inductor. You have a spirally wound coil as you see here, and then there is some kind of a ferromagnetic core that you see in the center. Now there are some objectives for doing the simulation. The first objective is I would like to understand what is the inductance of this particular device, and the second thing is I would like to understand what is the magnetic flux distribution inside my model, mainly inside my core, and finally what are the induced currents in my core and so on. Okay. Now what is the philosophy of doing simulation inside EMS? Now now this goes back to what is CAD embedded simulation. Now CAD embedded simulation is a terminology whereby the simulation resides right inside your CAD package. For example, one can design this kind of ferromagnetic core inductor using a CAD package like SolidWorks, which is what we are using today right now. Okay. Now as far as SolidWorks is concerned, you can model your components as different parts. As you see here, there is this core and there is the coil as well, and then as soon as you do your model, you can go to EMS and simulate your model immediately. Now the first step in doing any kind of EM simulation is to create what is known as a study. So one can create like 6 different study types are available inside EMS. Now inductors primarily function under AC or some kind of a oscillating pulse type of current or voltage. So the appropriate studies for inductors are going to be either AC or transient as a function, anything that varies as a function of time. Now the program allows you to do compute the circuit parameters. So ideally a field simulation is used to simulate a component that is being designed specifically for a purpose, and once that design is done, the circuit parameters like the inductance, the flux linkage, etc. Will be computed, and then this circuit can, these values can be actually used in a circuit simulation type of software, and then thereby you can standardize this particular design into your circuits, and then go about doing your circuit analysis and so on. So computing circuit parameters is very useful in giving you some of the circuit parameters that is required for you to substitute this inductor into your circuit simulation. As far as coupling is concerned, the main thing that might be of interest to people is the thermal coupling. In this case, we will just not couple in this particular problem, and we will create a study. Now once the study is created, the next step that is involved is in creating the materials of the components that comprise the inductor. Okay. First is the coil, and the coil is made up of copper. Assigning materials in EMS is extremely simple. One can go ahead and say apply materials, and then pick materials from the EMS predefined material library. Now we have conductor materials, we have steels, we have ferromagnetic substances, etc. So it's an exhaustive material library where you can apply material. It's also a customizable material library in which you can create your own materials and use that for simulation. Okay. Next is we talk about the core. Now core is made up of electric steel, And we also, you see a little lightning mark next to it. That means that one is interested in computing the induced currents in this particular part or geometry. Okay, so one can actually turn on or off the ADFX, and then in this case we are turning it on so that we can compute the ADFX. That's as far as the materials are concerned. There is only one other component that I hid it on purpose. Now I'm going to show that, and that's the concept of air. Okay, as you guys know that the magnetic field does not exist only in the metallic part and the ferromagnetic part, but also in the air surrounding it. So to be able to capture that magnetic field, one needs to model what we call as the air. So that can be done easily inside SolidWorks, and you can assign a material air for that particular geometry. Now once that's done, really we can get that out of the way by hiding it. Although it is included in the simulation, it's something that we can hide right now so that we can focus on the model at hand. Now once the materials are defined, the next step is in defining the coil. So let's go ahead and define a coil. So a little preview of how the current is going. So basically you select the components that comprise the coil. You select the phase in which the current enters. You select the phase in which the current exits this particular coil. In this case, this coil is what we call as a solid coil. Okay, and it's a current driven. In this case, we just input the RMS value of the current that the coil is going to take. In this case, it's 15 amps. Okay, so once the coil is defined, the program now knows the current that is going into the coil and is ready to compute the magnetic field distribution and so on. So this is a finite element based simulation, and one of the main ideas of finite element based simulation is the creation of what is called as a mesh. Okay, mesh is nothing but discretizing or splitting this geometry into small triangular elements, and then in all of these triangular elements they have what is called as nodes, and the Maxwell's equations is solved in the nodes as well as the and the results are produced. Okay, now if you want to visualize the mesh, I can show it, but I do want to let you know that EMS has a completely automatic mesh generation process which takes care of meshing for you. So, and having said that, we also have mesh control tools that allow you to optimize and manage your mesh in different sections of the geometry. Okay, now I have pre-run this simulation before this webinar, so let's go and delve right into the results. Okay, the results are organized inside EMS in the form of result tables. In the result table, you have first of all the main important thing that we came in here for in this particular simulation is the inductance value. You can see here that the inductance is about 16.7 microhenry. Okay, so the inductance value is computed automatically by the program. In addition to the inductance, we can also compute the flux linkage that is computed here. The impedance, both the real and the imaginary part, is also computed by the program. We also compute the solid loss both in the core as well as in the coil. Okay, now coil is just the I squared R loss. It's directly proportional to the square of the current that is injected into the coil, but the core is a little bit more tricky, and the loss that arises due to the core is due to the induced currents and so on. So EMS can compute the losses in the core, and you can notice here that that's really quite negligible. It's about 1.5 10 to the minus 2 watts. Okay, and probably the objective is to find out a suitable current where the core loss is not too high. And also the resistance of the coil is also computed by EMS. So if you have a complicated geometry of the coil as you see here, we automatically compute the resistance for you. So this sums up what we call as the circuit parameters, because you have the inductance value, you have the resistance value, you have the impedance, flux linkage, etc., and also the losses. So pretty much all of the parameters that one would need to represent this particular inductor into their circuit module will be given by EMS. Okay. Now let us now focus ourselves into some of the 3D results. Okay, EMS can give you things like the magnetic flux density. Now this is the magnetic flux density inside the core as a section plot. Okay, so EMS can compute the magnetic flux density and its values. You can see that it's about 0.18 Teslas is the maximum B field here in EMS. Okay. In addition to it, EMS can also compute the current density. Now we can see the current density. This is the induced current in the core, so which is of use to people. So just, and also one can take a look at it from the perspective of a vector. So you can see this is the current density in my model as vector. So you can see that there is a circulation of current going on in the coil, and also there is some induced current in my core. So I can decide to show only components of interest to me. So for example, if you want to find out what is the current density as vectors just in my core, ferromagnetic core, so I can actually show that, and you can look at the value of current density with respect to the various phase angles. Okay. So, so this is really the induced current that is responsible for the core, the loss, the solid loss of the core, as well as the heating of the core. And finally, the loss densities also can be plotted. Now this is the loss density. You can see the I squared R loss in the coil, as well as the losses due to the induced current in the core. Yeah. So the EMS gives you a good idea both as well as the quantitative ways of getting your model, getting your results in the form of inductance, etc., flux linkage, etc., as well as some kind of a very qualitative 3D visualization way of looking at what is happening in and around your model. Okay. With this, let us now go towards the next model. This is more of a laminated core inductor, some kind, you know, some people, it has two different coils, the primary and secondary. So in terms, it is some kind of a transformer as well, you might say. And here we do a very similar simulation as before. Okay, we created the study. Now this study, if I look at the properties, we are asking it to compute the circuit parameters. And also in this, and the frequency of interest, as in the previous one, it's about 50 Hertz here. And finally, it is coupled to a thermal simulation. Now, EMS coupling to thermal can do both steady state as well as a transient type of simulation as far as thermal is concerned. So in this case, one is interested in the steady state final temperature distribution in the model. So we would stick ourselves to the steady state thermal. Okay. Now the materials, as before, have been defined here, and once the material is defined, one can take a look at the coils. Now there is a small difference in the coil with respect to the previous problem that we saw here. Now we have what is known as the wound coil. That's the concept that is going to be used here. Now if you look at here, you can see the arrows that show the current going through the primary coil. So you select the components that comprise the coil. You select the phase through which basically the cross-sectional area through which the current circulates. Okay. Now this is a wound coil. You contrast it to the previous problem, which was a solid coil. Here there is several different windings of copper that make it a coil. So you can make it current driven or voltage driven. You can tell the wire gauge of the wire that is used to wind, give the number of turns, and also the RMS value of the current. Now this basically defines the coil. Now the primary coil is the one which is excited, as you see here, and in the secondary coil, this is just open circuit where I would just apply zero current, and it has twice the number of turns as the primary coil. Okay, so it's just an open circuit condition for this particular inductor. Okay. Now, with respect to the material, there's something that I did want to bring up is the ability to have laminations. Okay, so now in this particular material, we have laminations along the z-axis, as you see here, and what we have is also called as a stacking factor, and that represents the percentage of iron when compared to the percentage of the insulating material that is there between these stacks of iron. Okay, so stacking factor of 0.9 means that 90% is comprised of ferromagnetic and 10% is the insulating. So the stacking factor can be anywhere between say 0 and 1 denoting that there is no lamination, and 0 really is meaningless, but a low value means there's a lot more insulator or less iron. So for most laminated cores, you know, somewhere between 0.6 and 0.9 will be the stacking factor based on the application. So once the laminations are been taken care of, we are ready to take a look at some of the results. The only other thing as far as the thermal is concerned is the ability for setting up what we call as a convection boundary condition. We tell that any of these faces that are in contact with the air is convecting at a natural convection with a convection coefficient of 10 watt per meter squared Kelvin with an ambient temperature of 300 Kelvin. Now, as far once these this is all is required to set up this problem, now we are ready to take a look at some of the results. Now, as before, the result table is quite rich and it contains all of the data that is needed as far as characterizing your inductor is concerned. Now you see that the solid loss in the core is about 5 watts. Okay, we also compute the winding losses in the windings. Okay, obviously the secondary coil hardly has any current through it. Is just a little bit induced, so there is not much, but the primary ones obviously have some amount of winding loss. The resistance of the coils are computed. The inductance, the matrix in this case, the self-inductance of the primary coil, the self-inductance of the secondary coil, as well as the mutual inductance between the coils are also automatically computed by the program. The flux linkage for both the coils are computed, and as well as the coupling coefficient between the coil. So if you look at it, and finally the induced voltage in the primary as well as the secondary coil is computed by the program. So really a lot of these engineering quantities are available in the form of a result table. Now we'll take a look at some of the 3D results. So we'll start with the magnetic flux density. Now this is the distribution of the magnetic flux density in the core. And then you can see that it's about 0.8 Teslas is the maximum, so it's not really, the core hasn't quite saturated for an electric steel type of thing. And one can also take a look at the current density. Now this is basically the current density in the model, and the induced currents in the core is being represented as well as the current that is going through the coil. Okay. And finally, you can also take a look at the loss densities. Now this is the loss, the solid loss mainly happening in the core, and one can see the plot of the loss density. Okay. And as far as temperature, the thermal is concerned, one can plot the temperature of the core. Okay. So you can plot the temperature in the core, and this really gives you the plot of the temperature in the core. So there's really very little losses and hence the distribution of temperature. So the temperature rise is very nominal when compared to the ambient. So this is the plot of the temperature and so on. Okay, pretty much with this I conclude the demonstration part of this webinar. I hope this would have given you a good idea of what is possible inside EMS. Obviously what we touched upon here is a small fraction of all the capabilities that the software provides, and I encourage you to look at our website and our YouTube videos and talk to us regarding your particular application and we'll be very happy to tell you how we can help you with it. Okay. Just as a recap of what we saw about really why EMS, some of the things that I showed you here are probably just described as words. Now, I would say the primary reason for considering a simulation package like EMS would be its very powerful CAD integration. So we saw the integration with SolidWorks, but the same happens with Autodesk Inventor as well as SpaceClimb. So it's well CAD integrated. It also has multiphysics coupling. Today we saw thermal, but there is also motion. If you do any kind of solenoids which have motion, you have motor simulation and so on. We couple it to a motion, as well as if you want to do the thermal stresses due to the temperature, we couple it to structural as well. As you saw, it's really easy to set up. There's a very short learning curve. So the objective here is really to focus on creating your design. And then as soon as you do that, simulation is quite easy and straightforward as to follow. Okay, and also we have a lot of learning resources that can make you productive right from day one, and those are online tutorials, some YouTube videos. We have an application called Demo Viewer with numerous real-life examples, and we also offer web training. Okay. And finally, we are trusted by over 400 customers worldwide use EMS, and here's just a snapshot of some of the people who do use our product. Okay. With this, I will turn on the mic to my sales manager here, Adam, who will take you through the last concluding comments, and then we will go over Q&A. If you have any questions, please type into the chat window. I will be observing it and will be answering it towards the end of the presentation.
Okay, very good. Arvind, thanks so much for the presentation. I hope you guys enjoyed what you saw and learned quite a bit today. But we'd like to tie some kind of a promotional items as far as the product is concerned. In order to do modeling inductors, you probably need, or you'll need basically EMS magnetic, and if you care about the thermal, you need also EMS thermal. As far as price, if you acquire both of them, EMS magnetic and thermal, they're at $20,000. But for attendees of this webinar, they will be able to acquire it for $12,000. So I repeat, $12,000 for EMS magnetic and thermal, and $10,000 for EMS magnetic only. So you guys can ask us about this offer after the webinar and get in touch with us on adam@emworks.com or comment this number. Will be able to more than happy to help you. Now, of course, sometimes deciding from just seeing a webinar is not enough to decide if you're gonna buy, if you need it or not. For that reason, you guys can also email me, and we'll allow you a 15-day trial, full trial with support. That way you get the feel and of how to do some modeling, how to model some inductors or any other application that you guys might have, and be able to take advantage of the offer on a timely manner before the end of the month. So this offer is good until the end of November. I repeat, 10,000 instead of 15 for EMS magnetic, 12,000 instead of 20 for EMS magnetic and thermal, and plus a 15 days full functional trial with support to help with the decision if you want to add the product. I would recommend also visiting our website, www.emworks.com, and seeing some white papers and customer testimonials. They're very telling. On our YouTube channel, there's a lot of videos there that you guys can see. But if you have any particular questions, feel free to send an email to me at adam@emworks.com or to my colleague Jonas at emworks.com. Thank you so much, and let's go now and see if you guys have any questions, be it commercial or technical.
Okay, thank you, Adam. There are a few questions, and I'll be very happy to answer them. Now, our inductor designs for high power, high frequency range from 2 to 5 megawatts and a frequency of 25 kilohertz, 25 kilohertz possible for modeling. Absolutely. All are low frequency. Let me just quickly cycle through here. If you see here, the EMS package that I showed you here pretty much has the ability to model anywhere from a few hertz all the way to a few hundred megahertz. So 25 kilohertz frequency is absolutely possible, and high power inductors for several megawatts is also possible. There's no real problem with respect to that. If you have a design and you put the right excitations, etc., with the 25 kilohertz frequency, we will absolutely be able to solve that particular problem. Okay. If you get into a few hundred megahertz, and that's really where we may have to resort to the other package that you see on the right side. But as far as kilohertz are concerned, we will have no problem. And EMS does take into effect the skin effects produced due to high frequency, so all of it is automatically considered in the product. Now there is there is also a question related to price about what Adam had earlier said.
Yes,
the price
that's true. That's true. I mean, that price, I mean, does not include SolarWorks, so you still have to acquire either SolarWorks or Autodesk Inventor or Space Claim to be able to use EMS, but unfortunately, that price does not include SolarWorks. Thank you.
Mm-hmm. Now, as we said before, a recording of this particular webinar will also be sent to everybody who has registered, so not just the attendees who came in today, but for everybody who had registered. So feel free to view them later if you need other information, and also share it with...
There is one more question.
Sure.
So this is power application for inverters, so I don't know if this is a question.
Yeah, certainly that's not a problem. I think this high wattage inductor for inverters, we will simulate. It all depends on the frequency, and at 25 kilohertz, I think we will have no problem in doing that. There is also a question about induction heating. Yes, do we do induction heating? Absolutely. I can model a coil and have and pass current through it at a particular frequency and use it to compute what is the heat generated. You can use it as an induction heater basically, and one can do that, and we have some examples highlighting induction heating in our trial version. So we do induction heating kind of similar applications. You can find out the induced current on the workpiece, and even one step further, you can even set up a thermal simulation to find out what is the temperature distribution on your workpiece. So if you have a model of induction heating, we will be able to handle that application. There is a support for design under. There is a question that talks about design under contract. I think probably this question refers to consulting. Yes, we do offer consulting services. Please contact Adam for that. It is job specific, and based on your kind of needs, we will evaluate the time taken and the cost, and then it's basically per customer based on the project. So we will be happy to answer questions related to consulting, but please, we'll take it offline from the webinar, and you can contact us about it.
This is Adam again. There is a question regarding the consulting. We are based in Jacksonville, Florida. Okay, we will send you a contact name and phone number, so if you please share that with him. But being in Florida is not an issue. We can always do everything over the web. And please contact me personally, adam@emworks.com. Phone number 514-612-0503. I repeat, adam@emworks.com. Phone number 514-612-0503. And you need training for 10 engineers. Okay. Absolutely, you can always talk about that. Training for 10 engineers, we can talk about that for sure. So please do contact me, and I'll be more than happy to help you on the matter and address your needs.
Okay, with that, we do come to an end of this webinar. On behalf of EMWorks, Adam and I thank you all for spending your valuable evening listening to this webinar. I hope it was quite informative and gives you a sneak peek into what EMS can do for your needs, as basically your electromagnetic design needs. And we strongly encourage you to look at our website, our YouTube channel for more information, and please do not hesitate to contact us if you need any further information on the product. Okay?
Thank you all. You have a great evening, good afternoon, great evening, great afternoon, and a great morning for some others. Bye-bye now.